in 2002 with a thesis on tidal dwarf galaxies. Then he moved to Durham to work with Tom Shanks on cosmological surveys and galaxy evolution. And in 2005, he joined the 3D spectroscopy program at the AIT in Postdam, Germany. And since then, he's been working on the MUSE project.
Okay, thanks for the introduction. So I'm happy to be here today and have the opportunity to talk about the MUSE project. So MUSE, a giant integral field spectrograph, is what I call the talk. So I'll tell you a bit about the MUSE project and about my involvement. I also highlighted Roland Bacon, the PI of the project, as a co-author because I took several slides from him directly. But many of the results are, of course, a collaborative effort of the whole MUSE team. And the MUSE team, the consortium, is, well, 7 institutes are involved, including some parts of ESO. As I said, the PI is Roland Bacon from Lyon. It involves, in total, 100 people, maybe a bit less, maybe even more. So distributed over management tasks. There are engineers involved, optical designers, software developers, and astronomers. I myself, I'm somewhere located between these 2 items. So I designed and developed the data reduction software for MUSE, so developed at least large parts of it. And I'm an astronomer by training, as you heard, so I'm more and more involved now with the science preparation for the guaranteed time of the project. So some other parts of ESO, about 15 to 20 people, I think, oversee the projects. So they are controlling other parts of ESO, which is kind of funny. So there's basically 3 main parts of the talk that I want to go through. First, I want to tell you something about the instrument, how it came to be like it is, and what the status is of the instrument now. As I'm heavily involved in that, I want to tell you a bit about data handling, data processing, data reduction, and so on. And finish with some science prospects, so what you can do with MUSE. So, the instrument. So the basic idea, the design driver of the instrument was to study galaxy evolution at high redshift, or even over large parts of the high redshift universe. So you can do that several ways. The way that I think the designers of the instrument, the people who were involved from the start, thought about most was to do spectroscopy of high redshift Lyman alpha emitters, which you can do via several techniques. Mostly used today is probably the narrowband imaging technique, where you have the advantage of a very wide field, but you also need spectroscopic follow-up to confirm the Lyman alpha emitters to be real Lyman alpha emitters at the redshift that we thought they would be. You can instead use scanning techniques where you then do not need to follow up spectroscopically because you can scan through the whole line. Or you can use integral field spectroscopy, which has a relatively narrow field, up to 2 arc minutes or so for the widest field instruments at the moment. But you gain a lot of depth, so a long wavelength range that you can see Lyman alpha. And you also gain, compared to narrowband at least, high sensitivity due to the spectral resolution, where narrowband filters are usually several tens of angstroms in width. Here you have a resolution of 1 angstrom or a bit more. So you gain a sensitivity of a factor of 10 or so in detecting fainter Lyman alpha emitters. So to detect emission lines to the faintest limits possible and to the highest redshifts possible, you want an instrument that is very efficient, and to reach long exposure times you need also a very stable instrument. You need at least medium spectral resolution so that you can look between the sky emission lines in the red part of the optical spectrum, and you want a long wavelength range to cover large depth of the in redshift. And you also want to have high spatial resolution because the Lyman alpha emitters are mostly point sources, and so you can gain signal to noise by having smaller spectral elements. So that leads to instrument parameters, basic instrument parameters like this. So MUSE will have a spectral range from over a wide range in the optical domain, so from 4,650 angstroms to about 9,300 angstroms, with a resolving power of about 3,000, so a little lower in the blue part, a little higher in the red part. The instrument's main mode is the wide field mode, where you will have a field of view of 1 by 1 arc minute, which is sampled with 0.2 by 0.2 arc seconds on the sky. So you have something like 90,000 spexels that you are recording at once, and to get the resolution, you need at least 4K CCD, and actually to get the sampling done spatially, you need to distribute this over 24 CCDs. So each exposure will have something like 370 million pixels. So I said before, the spatial resolution is a factor. Normally, if you are seeing limited, you have something like, well, median seeing at parallel of 0.65 or so arc seconds. So you may want to improve on that by using AO. And the gain here is to boost the n-squared energy that you record in one element by a factor of 2. That limits the sky coverage a bit, because you also, for AO, you also need tip tilt star that is not available anywhere at the right brightness. But at least large parts of the sky should be observable with AO. So faint limits from MUSE means something like a IAB of 25, or the full resolution for very long exposures. So the number to keep in mind is about 80 hours is what is designed for. And as we want to observe Lyman alpha emitters, preferentially you're talking about a limiting flux, about 4 times 10 to the minus 19 ergs per second and square centimeters. So to get that, you also need very high throughput. There's not only the wide field mode in MUSE. It turned out early in the design that with just one small optical element, you can also change to a narrow field mode. So for, well, the wide field mode you can of course also use without AO, because AO will not be available 100% of the time, just because atmospheric conditions are not right, or because maybe technical problems, I don't know. So you can do that without AO in seeing limited mode, and you can, for the wide field mode, have this moderate seeing improvement using ground layer adaptive optics. And then there's narrow field mode, which can only be used with AO, or only makes sense to be used with AO, which will have high order AO correction, which will be mostly effective in the red part of the spectrum. And it just works that you change the spatial scale of the instrument so that you sample not with 0.2 arc second, but 0.025 arc seconds. And you get a field of view of 7.5 by 7.5 arc seconds. Well, as another mode, there's also the standard wavelength range, which starts actually at 4,800 angstroms. There's a second order cutoff filter built in so that you don't incur second order overlap in the red, which would be disastrous probably for high redshift work. But there's going to be an extended wavelength range with the numbers that I cited earlier, where you do get a second overlap in the red part, depending of the spectral energy distribution of your source, worse or not so bad. So for those of you who don't know integral field spectroscopy very well, I guess there are not many people here that don't know about that. Anyway, there are in this slide by Jeremy Ellington Smith, that's shown in many IFU related talks. You can see several techniques. So lens thread arrays, fiber arrays, where you always somehow reconfigure the focal plane of the instrument to in some kind of slits or slit-like formation, and then you disperse it through the spectrograph. So for MUSE, the image slicer was chosen, probably because, as it says here on the slide in the lower right, that this gives you the highest information density for on the CCD and also in the output data cube. So how does it actually work for MUSE? As I said, you need 24 CCDs to record all the information with sampling that you want. So there's actually two steps involved in dividing up the field of view. So if you observe a galaxy like this, which in reality is actually much too big to fit in the MUSE field of view. Anyway, if you want to observe a galaxy like this, you first split up the field of view, not in 4 subunits, but into 24 subunits. And of each of these subunits, that's then fed in onto the, from the field splitter onto the image slicer, which is this here. It's also called image dissector array, IDA, and then onto this focus mirror array here, which then feeds the light into some kind of pseudo slit, which is then going through the spectrograph in the end. So what does the instrument actually look like? This is an animation of, I think, a bit older rendering of the instrument on the VLT Nesmith platform. I think I show it again. So you can see that there's the main structure in gray, electronic cabinets around it. This would be the side of the VLT, so you're looking into the instrument like this, and well, some other parts are within these yellow boxes. So a bit more in detail. This is the rear view of the instrument, and so you see here first the instrument main structure, which is this rectangular shaped thing in the middle that you can hardly see, because from this side you can see the 24 spectrographs, which, well, you can always see the CCD end of the spectrographs with the dewar attached here and the vacuum cooling system and so on. At the top there are the CCD controllers. Here you can see the integrating sphere of the calibration unit, and I think an electronic cabinet, and here somewhere on the side. So if we turn this around a bit, look from the side, so you can see the VLT Nesmith flange here. And if we look from the front, you can actually see, in this rendering, the covers were removed, so you can see part of the optics. And so the main structure is this one with these cylinders here containing the spectrographs. Just to guide you a bit through where the light passes through the instrument. So the VLT focal plane is somewhere here, enters the instrument, goes through the derotator, because you don't want to, I mean, the instrument is very heavy, almost reaches the limits of what the Nesmith platform can handle. So you want to compensate for the telescope rotation by having a derotator, a small element at the front. And then it goes through this part which selects either wide field mode or narrow field mode in the 4 optics. Then it goes on further into the splitting optics, so through here, and only one light ray is basically shown. So this is the field splitter. You can see these 24 mirrors that are stacked on top of each other. And so from one of these subfields, the light goes into here, into the relay optics, and then down to the respective spectrograph. Unfortunately for the, I don't have a rendering that shows the light inside the spectrograph, but this is what a real image slicer looks like. So you can see there are 4 stacks of 12 mirrors top of each other. And in the instrument, it sits somewhere here at the one end of the spectrograph. And in reality, this is in the lab in Lyon, where you can see the image slicer here, and then the component on the other side, that's the focusing mirror array, which then sends the light into the spectrograph to be dispersed. There are 24 spectrographs. That is done by this field splitter, which is, whoops. Here by these mirrors. So each of these mirrors guides the light to one of the spectrographs, basically. It's just that only one of the light going to one of the spectrographs is shown. There are similar lights going here and there and on the other side of the instrument. The spectrographs are all identical. Okay, because I'm from Postdam, from the AIP, I show you what the spectrograph looks like in reality. That's basically this black thing here, where you have in the final instrument, then the slicer arrangement on this side, the volume phase holographic grating somewhere in the middle, and the CCD in its duer at this end. Well, at AIP we do detector testing. So we have one spectrograph that is used to test all the, well, basically the silver parts here at the end. And so we are not using the slicer itself, but some kind of mask that is illuminated, so this doesn't look like before. At AIP we also built the calibration unit for MUSE, which sits, as I said, here at the top of the instrument. You can see here the integrating sphere, and the real one looks red instead of black as in the rendering. You can see some lamp housings here with the light guides and mechanics and electronics on the side. Yeah, I said that performance and throughput is very important for this instrument because we want to reach to the faintest limits. And the performance of the spectrographs is tracked in a sheet like this. The interesting part, actually, it only shows 4 so far, but I think there are more tested by now. This is from a few months ago. So the interesting part is this. You can see here the throughput. So the horizontal lines are the specifications in the different wavelength ranges, in the red, blue, and green wavelength ranges. And you can see that the dots representing what was measured with the IFUs is actually above all of them. So the throughput is better than expected. And similarly for the image quality depicted in this diagram, where of course you want to be below the specifications here, and that is true for also for all these 4 IFUs shown here. And actually you can compare this with other ESO spectrographs. This is a plot that Roland created using the information that each exposure time calculator at ESO provides you. So it includes the total throughput of the instrument plus the telescope, but without the atmosphere. And you can see MUSE is the black line here, and it outranks basically all of the other spectrographs. Although some X-shooter people were not too happy when we showed that because they thought it should also be higher, the green lines. But if you compare that to other IFUs, like the VMOS IFU here in purple or the Flames IFU in blue, you can see there's a gain of at least a factor of 3 or even more over much of the wavelength range. Okay, so for the instrument part, that leaves me with the timeline. So the past milestones that we passed were in the design phase, like the preliminary and final design reviews that were big meetings at ESO. We passed that, and currently we are in the so-called manufacturing, assembly, integration, and test phase, or MAIT for short. That will end with the preliminary acceptance in Europe in, well, next year. And then we'll go with the instrument to Paranal, where we'll hopefully get then after successful commissioning, the preliminary acceptance in Chile in early 2013, and then the observations hopefully start in April 2013. Before you get excited too much, there's a small limitation to that because the AO will come 1 to 2 years later. I think that's the current estimate. So we go on to data processing. Just a short remark about the data volume. So you have 24 CCDs, 4K by 4K, and so a raw exposure is something like 800 megabytes. This is not outrageous. I mean, you reach it with the largest current images too. And also the typical data rates of something like 30 gigabytes a night of science data plus calibration data. Depending on how many calibrations you want to do, you can get much higher than 100 gigabytes, but something around 30 gigabytes for science data and 30 gigabytes for calibrations data should be realistic. What is a bit unusual maybe is that the reduced exposure is not really reduced, but inflated a lot. That is due to, well, you start with 16 bits, you blow it up to 32 bits, then you add variance to that, maybe bad pixels if you want to save it in the Euro 3D format, and you end up with something between 3 and 5 gigabytes. So on a standard laptop today, I think it's not, a standard laptop of today would not be well suited to display this. The data format looks about like this. So this is 1/24. It's, well, a 4K by 4K CCD that's read out on 4 ports. So you get 4 different bias levels, overscan region in between. And this shows, well, each of these vertical strips is coming from one of the slices of the, one of the slices. So the blue part is at the bottom and the red part is at the top, and this is a simulated exposure from the so-called instrument numerical model that is developed in Lyon. So it shows really where the skylines should be. It shows where the throughput is highest, somewhere in the middle. And you can see some vertical brighter lines, which, like here, there, which shows continuum objects. So there are 3 continuum objects in this data, and 1 Lyman alpha emitter, which I don't think you can see like this. So I'm going to highlight it. It is somewhere here. And if you blow that up, you can actually see that it's, well, visible here and here and here. So I'll show you later how this looks in a reduced format. So the goals of the data directional software of the pipeline are these. So you want to fully reduce all the exposures without creating a backlog. So you have to handle all the 30 gigabytes per night. So you have to reach a certain speed, which basically also calls for parallelization of the code. And you want it to be at least largely automated. You want to know where the pixels are so that when you interpolate, you can throw them out, or at least know afterwards where they are. And you want to propagate error information so that you have an output variance and can read off signal to noise basically at every point. You also want to have the best data quality possible for the widest variety of observing programs. I mean, that's really a tricky part, but I think it was the right decision now that we go the way that we resample only once. So at least we do not enhance the resampling noise with multiple resamplings as it was done in other data reduction softwares before. So if you have handled ISO data, then you know you have to work with ISOREX, Gascano, or in the future maybe Reflex, which are calling plugins that actually do the work for the data reduction. They are called recipes in ISO speak. And for MUSE, we'll have two processing levels. One that works on the basis of the data from single integral field units. So it does the calibration like, well, the usual steps, bias, dark, flat, wavelength calibration, and then combining, well, applying the calibrations to the science data. And then what we call science processing or post-processing, which then involves the data from the whole instrument. So the idea was that you can basically parallelize the first part trivially just by calling the same process several times with different IFU numbers. And this one then has to be parallelized for real, and we have chosen OpenMP to do that. Okay, a few words about how it's achieved that we only resample once. So this was previously called somewhat enhanced approach. So you go from CCD-based images to what we call a pixel table fairly early, once you know all the coordinates, because then you can fill this table with the coordinates x, y, lambda, and the actual data value, the pixel status, the variance, and plus some helper coordinates. So you have a table that contains all that for all the pixels, which blows up the data volume enormously. But then you can, all the transformations that you have to do on the data to remove atmospheric effects and other instrument-specific effects, you only need to change the coordinates, but you don't need to touch the pixel values. You don't yet need to interpolate. And only the final resampling at the end then converts it to a data cube that you can actually use, or even, well, you can collapse the data cube then and create a white light image or something like that. The drawback is that it relies on the final resampling, and that's going to be slow and requires a lot of memory. And for some intermediate calibration steps like standard star handling, you need to resample in between. And the main drawback for me is it's very hard to debug, because when you see some artifact in the final data cube, you have to go back through all the steps to find out where it came from, and that's not easy. But the advantages are clearly that when you otherwise resample multiple times, you add noise each time, and you also mess up your error propagation, and so we get correct error propagation. And testing shows that for MUSE it works, and there are also some other projects which use it, like a VMOS pipeline that Daniel Kupko at ARP wrote that also uses a similar approach, and I think the KMOS project is also still following this approach. So just to put this into, well, not really visual, but some more clear impression. So you start with this, then once you know the wavelength, you can enter the coordinates within the field of view of each pixel. You transform the pixels into such a table. And if you then have to shift the data because you want to add to another exposure or something like that, or scale it because you're doing, I don't know what, you just change the first two columns. And then if you do an astrometric calibration, for instance, you just, again, change the first two columns from pixels to right ascension and declination. So you don't need to change the values themselves and only interpolate at the end. And so this is what this two-step approach came from. You have the basic data reduction, which applies the calibrations and especially goes from the image-based format to the pixel table. And then you have the post-processing, which does all the calibrations with on-sky exposures. And finally resamples the data into the output cube and integrated images. Yeah, how well does that actually work? So this is a test that I did some months ago with simulated data. I showed you the raw data of this before, the raw data that went into the first image here. So this exposure, the simulated data contained 10 exposures of 1 hour with small dither offsets. It contained 4 objects, as I said, 3 continuum objects and a Lyman alpha emitter. And if you do some simple combination, correcting for the offsets with the pipeline, that already enhances the signal to noise. That's not really well seen in these exposures because the simulation itself already had some problems causing artifacts in the raw data, like these brighter backgrounds that you can see here. But I think if you look at this object, you will agree that the signal to noise increases from here. So what we are looking at is a monochromatic slice to the peak of the Lyman alpha emitter. So this is a continuum object, this is a continuum object. The Lyman alpha emitter is this one here. And this is with a single exposure, this is with 3 exposures, and the third one is with 10 exposures. And then you can do something additional, that you weigh the exposures according to their seeing, and then you enhance the signal to noise a little bit further, and you get more compact sources because you give more weight to the exposure with the best seeing. So this was data with only one of the IFUs. In the meantime, the simulation software has evolved and can produce data from all 24 IFUs. And this is the first data set that we worked with. And well, it was just here to show that the raw data somehow contains this rhomboid shape, which is due to some optical effects in the instrument. And after you run the pipeline, you get an almost perfectly rectangular grid of these sources. And they are, at least in relative terms, they are exactly where they should be. And they also have the correct full width of mux in the output and the correct flux in the output. So I'm pretty happy with how the pipeline performs on this. So if you're thinking about doing MUSE observing run and proposing for time in 2013, maybe you should also think to get a new computer to do the data reduction, unless you get someone from the consortium to do the data reduction for you. Might be an option. I said that the data rate is comparable to the largest images in use, but the data is clearly more complex to process. And you need a lot of memory. And because we use shared memory parallelization, it needs to be all in one machine. You cannot really make use of clusters. So for typical applications with a few exposures, like 3 exposures that you want to combine, you can do with something like 32 to 48 gigabytes of RAM. But if you really want to go as deep as the consortium does, you really need more cores than you usually have on a desktop machine and a lot more memory. But with that, then you can do data reduction of simple programs with in under 1 hour, but with a deep field of 100 exposures or so, it might take several days to a week. So that finally brings me to the science applications. So these are just a collection of science topics from phase A that you can also find on the ESO webpage if you want to look it up again. So it ranges from high redshift star formation of galaxy evolution to nearby galaxies, which I'm personally also excited about because it would follow some of the work that I've been doing the last years, to stars and resolved stellar populations in the local group and even solar system. One of the main points also to use an IFU is serendipity, and we very much hope that we'll discover some things that you didn't expect to be there and just by chance end up in a deep field or some other fields that we take. Just to highlight two science applications. So this is the Hubble Ultra Deep Field, which many of you have probably seen. So this is 3x3 arc-minutes. So if you overlay the MUSE IFU, it's kind of small, so you need 9 exposures to cover the whole field. But if you blow that up, this is the central 1x1 arc-minute, and if you overlay that with the MUSE field of view again, this is the the 24 IFUs. This would be the 4 stacks of slices that are in each IFU, and each stack of slices has 12 mirrors, so you're sampling each of these by 12 again horizontally. So you get a very fine sampling here, and even from smaller galaxies you can get several spectra. You can either combine them to enhance the signal to noise or derive spatially resolved properties of the galaxy, velocities, and so on. And you even access things which are not visible here, like the Lyman alpha emitters that I talked about at the start. They wouldn't show up in this image because it's made from broadband exposures, where just the noise over the whole wavelength range dominates the little signal in the line. So the idea with MUSE is that you can basically cover the whole history of the universe in one shot through different emission lines, Lyman alpha at the high redshift and the oxygen lines at lower redshift, and you can get the Balmer break over large redshift range. And the stability of MUSE then should allow observations up to 100 hours per field, so that you can really get spectra of very many objects. This was very first simulation from 5-6 years ago of a deep field exposure, where in simulations you just tracked galaxies within the 1x1 field arc-minute field of view, and they are color coded due to their redshift. So the reddest objects are at the highest redshifts, and the greenish blue objects are at the lowest redshifts. And there are 450 galaxies in this field of view at different redshifts. Current mock data that we are creating for so-called dry runs, where we simulate data, then feed it through the pipeline, and at the end extract objects. This is an easier step, just directly simulating it and what the output data cube should look like. So you take the actual UDF data, assign spectra to each of the galaxies that you find, and because you don't see everything in the UDF data, you take also objects from hydrodynamical models and add spectra there, and then you convolve everything with MUSE properties like, well, the spatial PSF, the line spread function, the throughput, and so on, and atmospheric parameters, and then you come up with a collapsed image like this. So this is the integrated light of 9 MUSE exposures and 3x3 mosaic of 10 hours, and you see lots and lots of objects in here. Of course, it's still idealized because it implies things like perfect sky subtraction and no resampling effects. But this is now used within the consortium to test tools to find and extract and classify objects within this data cube. Because, well, it's a 21 gigabyte file, so it has lots of data in that, and you need just automated procedures to extract all the data. Just one other topic that I'm also pretty excited about is that you can, if you observe resolved stellar populations, especially dense ones in the local group, like in globular clusters, you get lots of spectra at the same time from lots of different stars. And with MUSE, you should be able to characterize the stellar populations and measure velocities of the individual stars. And it looks something like this. I think this simulation has something like 1,000 stars in them over the 1x1 field augmented field of view. And with some standard methods that a student at Postdam, Sebastian Karmann, has developed now specifically for MUSE, you could basically extract all of the spectra. And even for a bit denser fields, if you have some priors like high resolution images, you can even extract a few more. The challenge is then to derive the stellar parameters, because you have the red part of the spectrum and not the blue one, which would also be very interesting for stars. But the long wavelength range should compensate for having only the red part and having relatively low spectral resolution for stellar work. Okay, so I leave you with a summary. I hope that I've convinced you that this is a major and very interesting instrumentation project, that the building of the instrument is proceeding well, and that the performance is going to be very good. And I hope I've also convinced you that we know what we do with the data processing, and maybe I've piqued your curiosity a bit about what science is possible with MUSE, and maybe you already have an idea what you could observe with this instrument. So thanks for your attention.
So we have time for a few questions.
I think this is a very exciting instrument. But I have a question about the optical design. I'm not sure I fully understand it. So you have a field of view of 1 arc minute by 1 arc minute.
Mm-hmm.
So first of all, you divide this 1 arc minute by 1 arc minute in 24 slices,
mm-hmm.
which means 2 point something arc seconds by 1 arc minute.
Mm-hmm.
And then before feeding the spectrograph, you take each one of these slices and divide them again.
Yeah.
To form a longest slit, that this is directly the input to the spectrograph.
Yes.
So you form thinner slices and then get a longer.
So you from each of the 24 subfields, you form you have these slices which are four sets of mirrors next to each other, and they are in each of these stacks there are 12 mirrors at the top of each other. So you get 48 slices per subfield. And each of these slices on the sky are 0.2 by 15 arc seconds.
2 arc seconds by 15.
0.2. 0.2 arc seconds.
If you divide 60 arc seconds field of view.
First you divide the field of view into
34.
These subfields of 2.5 vertically and 60 arc seconds horizontally, and then you divide that again into 48 subfields.
Can you show the image with the?
Well, maybe I should. Actually, that was the one near the end.
Yeah.
So these are the 24 subfields.
This is 60 by 60 arc seconds.
This is 60 by 60 overall.
So in vertical you have 60, 24 slices, so you have 2 arc seconds per slice.
Yeah, 2.5.
Yes, 2 point something. Yeah. And then you divide it, each one of the slices into 4 more, but each one of them is 2 arc seconds wide.
Each of them is 2.5 arc seconds high and 15 arc seconds wide.
So the resolution, the spatial resolution is 2 arc
and
seconds.
then you divide again.
That's my point. Then you divide again.
You divide again, and you get these. Each single slide is 0.2 arc seconds high and 15 arc seconds wide.
And you know mechanically how small are these slicing mirrors?
I should know that, but I think I've seen one, but I don't recall. It's not microscopic. They are it's millimeter or few millimeters.
I was impressed by the throughput. Where does the gain really come from compared with Force 2 or X-Shooter?
Apparently, I was told, from improvement in coatings over the last 15 years. Coatings are apparently much more efficient than they were 15 years ago.
There's not the detectors, for instance?
Well, detectors maybe a little. And maybe also there are small improvements in everything. I think the detectors actually not so much. Well, one of the tricks of the detectors was that to use detectors with graded AR coating, where you have, because each part of the detector will always be illuminated with the same wavelength. You can optimize the detector throughput at that wavelength. That makes some difference.
I have a question about the schedule from now on. You said that the instrument is expected to be accepted in Europe by mid next year, and then accepted in Chile by mid 2013. So which is the plan from the acceptation in Europe and in Chile? So you will ship the instrument to Chile and do several commissioning periods, or?
Well, the standard, I think, with ISO is that you have 2 commissioning runs. So we're hoping that mid next year will be preliminary acceptance Europe.
That means that you will deliver the instrument to ISO.
Runs.
So after the acceptance, the instrument will deliver to ISO. Or is it still up to you to do the commissioning?
No. Well, unless we have something to fix, it should go to parallel. And then there will be at least 2 commissioning runs. And then we hope that early 2013 we get the preliminary acceptance to start the first observing period in April 2013.
So this, say, half a year between the acceptance in Europe and in Chile is devoted to the 2 commissioning periods. Well, some budget time for doing something.
To shipment and what ISO calls parallelization, and yeah. And there is not only MUSE as a new instrument on parallel, there are some other instruments also coming, and there might be some scheduling difficulties.
The data processing will be done from one day to the next, or?
Well, there will be a quick data processing done after each observation. That's the standard ISO policy, that they can check what they call quality control parameters.
But this will not be the final reduction.
But that will not be the final one. So if you, I think it's, the standard ISO way will still apply. So if you are visiting for the observations, visitor mode, then you have to do the final data reduction yourself. If you do service mode, then the final data reduction will be done at ISO headquarters. Well, and the final data reduction at headquarters then is a few weeks later.
Any other questions? If not, so let's engage again.